Hello and welcome to my students. Today's lectures we have see the chapter structure of solids. In these chapters we have learned various types of the crystal structures, packing density of the crystals, some terms like the crystal lattice point, lattice constant, as well as the various crystal spheres like clothes pack structures. These points we have learned in these chapters. Now firstly we have see the structures of solids. The solids can be made up various particles. These particles can be formed by using various matters. It consists of tiny particles like the ions, atoms, or the molecules. And these particles can be associated with a certain amount of energy, which decide whether the particles will have more tendency of repulsion or the attraction between these atoms or ions. In this tendency, like attraction or repulsion, the interparticle distance will increase or decrease, or which in turn decide the matter they will exist in solid, liquid, or gaseous state. When energy is possessed by constituent particles, which is more than repulsive force of attraction between the two particles, they will remain far away from each other, and which results in gaseous state. We have compared these three states like solid, liquid, and gas. The force of attraction between the two atoms or ions in solid states, they are maximum, because the distance between the atoms and ions, they are very near to each other as compared to liquid and gaseous state. But the particles relatively very close to each other in solid state, and therefore they will result the minimum attractive will dominate the matter exist in solid state. In solid state, the constituent particles, they are very close to each other, and therefore they cannot be compressed further, and hence they are rigid and cannot move freely in random motion, and hence they have definite shape, definite volume, and definite low vapor pressure. Such solids, which are called as the true solids. For examples, NaCl, KCl, sugar, or the copper. This called as these true solids. But you know that the solid which lose the shapes on long standing and readily distorted by mild distortion process, which is called as the pseudo solids. For examples, glass, pitch, etc. But you know that also the solids like sodium chloride, sugar are not a rigid, but also it compressible, incompressible, and they possesses definite geometrical shape. Also, they have definite arrangement of these constituent particles throughout the whole three-dimensional network of the crystals, and hence it is regular arrangement of these particles in the solid. Therefore, they have sharp melting point, and which is called as the crystalline solids. The solids like the rubber, plastics, they have rigidity, means it is a incompressibility to a certain extent, but they do not have definite geometrical forms, and therefore they melt gradually on heating. That is, they not have a sharp melting points, and these solids which called as the amorphous solids. Now next points we have going to discuss some important terms that can be used in these crystals of solids. So first terms we can learn crystal lattice. You know the crystal lattice? Crystal lattice, it is defined as the regular arrangement of the constituent particles of a crystalline solid in three-dimensional space, which is called as crystal lattice. But this crystal lattice, we can see the constituent particles, for example atoms, molecules or ions, they of the crystalline can be arranged in a regular pattern, and hence position of this particle in crystalline solids, they are relatively one another. Next points we have see the lattice point. Lattice point means the position of constituent particle in crystalline solids relative to one another is usually represented by a points which is called as lattice point. And the next terms we have see are here the unit cell. Unit cell means it is defined as it is a smallest repeating unit in space lattice, or smallest fundamental building unit of these crystals, which is called as the unit cell. But you know that regular arrangement of infinite set of these lattice point, which is also called as the crystal lattice or the space lattice. And then space lattice can be divided into a large number of small symmetrical units. Now we have see some of these points, but also this figure are shows that 18th unit cell, and this 18 unit cell composed of infinite number of small unit which are adjacent by one another in three dimension. This figure now we have see is here. What is mean by the lattice constant and what is mean by the unit cell? This is a lattice point. It is another lattice point. This is a another lattice point. For this number of lattice points, we can join our here and to got the structures of the crystal in the solids. So this is a example of solids like a sodium chloride crystals. These green colored points or the position are called as the lattice point, and those parts which is called as a unit cell, it is a very smallest part of the crystals It is called as a unit cell. The next points we have see the lattice constant. Lattice constant, which is composed of a infinite number of unit cells, and each unit cell can be completely described by three vectors like the A, B, C vectors. This is one of these vectors, second vector, this is a third vector. So A, B, C vectors having a x axis, z axis and the y axis. They can be described by three vectors like ABC gives length of h of unit cell and angles like alpha, beta and gamma. This lattice vector and interfacial angle, this is a interfacial angles of these crystals can be defined in the lattice point are collectively known as the lattice constant or unit cell parameters. So in these crystals, these three vectors are there, these three vectors, and this is three angles alpha, beta and gamma. Those points which is called as the lattice point or the lattice parameters. But also the in real crystals, unit cells are three dimensionals. So we can discuss one by one. You know that the crystals are the three dimensional unit cell which can be stacked one by one directly in the form of the various phases and to form the structures. The unit cell must fill all space and which is imposed on the number of possible shapes for the unit cell, and therefore the number of unit cell can take 7 possible crystal systems. Like the first one are here, now we have see is a simple cubic structures. These simple cubic structures are it having all edges, they will be similar like a. Other systems like this hexagonal packed system, orthorhombic packed system, tetragonal, triclinic and monoclinic. One of these crystal they will be remaining as a trigonal system. So such a types of crystal lattice which is possible in the unit cell in crystal systems. These unit cell it too must have space filling properties, and such a unit cell are stacked directly. But the unit cell must fill all space. A restriction is imposed on the number of possible shapes for unit cell. Thus, the unit cell takes 7 possible space shapes as cited in these figures, like a simple cubic, hexagonal, orthorhombic, tetragonal, monoclinic, and triclinic structures. And these structures, firstly we have seen the in cubic unit cell is one of having the 4 three-fold symmetry axis. And in this simple cubic structures of the crystal, all having a equal distance, like A is equal to B, B is equal to C, as well as the all angles they are be equals, like alpha, beta and gamma is equal to 90 degree. In cubic crystals have the other symmetry element as the 3-4-fold axis passing through a centers for a definite the crystal. Such a type of unit cell constant are lattice point only at the corners, which is called as a primitive cubic cell, which is denoted as capital P, primitive cube. So this primitive cube found only the polonium crystals, which is found only the polonium crystals. Similarly, a body center lattice points, it can be denoted by the symbol capital I. It has extra lattice point at the body center. For example, sodium, potassium, vanadium, those metals having a crystal shows the body center lattice cubic structures. The face-centered cubic lattice or face-centered lattice, which is denoted by capital F. So this face-centered cubic lattice R, it is also a cubic unit cell having 4 3-4 symmetry axis. It contains the additional point in face-centered metals like silver, gold, aluminium, calcium, etc. Another type is a tetragonal unit cell, which is defined by a single C4 axis, for example, calcium carbide. Face-centered capital A, B or C unit cell, which is depicted in the following figures like this. And in lattice parameters are shown that A is equal to B, but B is not equal to C, and alpha, beta, gamma is equal to 90 degree. The orthorhombic unit cell in which all the angles are 90 degree, but 3 mutually perpendicular to C2 axis. See here the first primitive cell, primitive cubic lattice, it having all edges they will be similar. So it is simple cubic lattice or primitive lattice. Another is a body centered cubic, means one of these atoms they will present at the center of the cube. This is called as a body centered cubic. And face centered cubic means it has been found that all the face it have one of these points, lattice point. This is one of the face, so it is one of these lattice point are here. Second face, these points are there. This side face, it is one of these, and its back side, this is above are here and below is here. So total points, so total face, how much? 6 face are there. So 6 face centered cubic, as well as at the corner is 1 2 3 4 and 4 8, 4 plus 4 8.